In this last section of Chapter 4, we're going to look at some diagnostics on the least squares regression line. In particular, we're going to look at something called the coefficient of determination. Now, the coefficient of determination is r squared, which literally means the correlation coefficient squared. That's what it is. So it's another measure of the strength of a linear relationship. Now, it has a very formal interpretation that we're going to use regularly. That's a script right here. So you're going to follow that script. And this is probably the most rigid script in the entire course. It does not deviate from what is written here for any reason. All right, so we'll look at that script when we do in a problem in a bit. But suffice to say that the r squared value is basically explaining what percentage of the variation that we're seeing can be explained by the regression line. We're never going to find this by hand because we never find r by hand. And the stat crunch path for finding it is the same as it is throughout Chapter 4. It's stat, regression, and then simple linear. Okay, so we often write r squared as a percentage, usually by multiplying by 100 to turn it into a percent. In other words, you move the decimal 2 spots over, right? 2 spots to the right, right? That's what multiplying by 100 would accomplish. It's used more in upper level statistics, so you're kind of just seeing it now in this one section, so you are more familiar with it if you run into it in some other course. And it's really great when you want to compare. That's where r squared really shines, is in which explanatory variable has the most effect. In other words, when we're making comparisons for different models. Okay, so let's think about this for just a bit because these can get a little confusing because they both have the word coefficient in them. So the correlation coefficient is r. Correlation coefficient was from section 4.1. The coefficient of determination is this section, which is r squared. They both say coefficient, so you have to know which one's which. The r is the correlation coefficient, the r squared is the coefficient of determination. Now, both of these values measure strength, and they're both found with technology. So they measure strength, right? Strong, moderate, weak, that kind of thing. If you remember those terms from section 4.1. They both are found with StatCrunch, so we're not going to find them by hand. And they're both unitless, right? They both actually don't have units. No feet, no inches, no nothing. All right. Now, what about calculating them by hand, sort of? So if you have r, if you're given r in a problem, then you would just square it to find r squared. It's as simple as that. Now, on the other hand, if you're given r squared, let me separate this paper. Here. If you're given r squared, you take the square root of it. And it could be positive or negative. It depends on the relationship of the variables. So you'd have to look at the slope of your graph to figure out whether it's positive or negative. So I would say look at slope, because if your slope is negative, then the r is negative. If the slope is positive, then the r is positive. Okay. Now it has the same strength variable values as we had before, but the numbers are different. And that's because they're related. So the perfect relationship is if r squared is 1, which is over here. That's the perfect relationship. The strong relationship is anywhere from 0.64 to 0.1, and that actually comes from the old value. So the old value for r was 0.8, and if you take 0.8 and you square it, you get 0.64, right? So they are related to the other values. So zero point 0.8 was the marker for strong. 0 0.8 times 0 0.8 is 0.64. So remember, this is r squared. So the next value started at 0 0.5. 0 0.5 times 0 0.5 is 0.25. So this is the moderate zone, right, which is the 0.25. You can see the r squared is a little more basic. It's a little, it's just not as complicated because it doesn't have a left side and a right side the way that the r graph does. It has 0 right here, right? There's 0. And it doesn't ever get any lower than 0 because it's squared, right? It's impossible for a squared to have a negative value. So it has the same relationship markers that R did, but it's a little bit simpler of a graph. All right, so let's take some graphs. These are actually the same graphs we looked at in section 4.1, but now we're going to associate them with their R squared values here. Okay, so R squared equals 1. You'll notice there's actually 2 of them that have R squared equals 1. It's right here and right here. They would have the same R squared value because they're both perfect relationships. Technically, this is perfect positive and this is perfect negative. But you only know the positive and negative by looking at the slope. It's not something you just know inherently. Right? R squared doesn't give it to you, in other words. R does. R tells you positive or negative. R squared does not. All right, what about 0.9? Well, 0.9 is a strong relationship. And the strongest relationship out here, right, the points are most tightly clustered right here. So this is r squared equals 0.90. This is a strong relationship. Obviously not as strong as the perfect relationships, but perfect relationships are not something we run into in statistics as a general rule. They're an algebra class thing, which we actually just answered this question down below. B is the strongest relationship because the r squared, which is 0.90, is the highest value. And also, the points are the most tightly clustered on the line. Right? Remember, that's how we measure strength visually. You want to look for how the points are clustered along the line. And of course, the perfect ones are exceptions to this. That's why it said besides the perfect ones, right? Because the perfect ones are the best, but we don't generally have those in a stats class. They're more an algebra class trick. All right, so we got to keep going now. What about 0.69? 0.69 is also strong, right? That's just not as strong because 0.64 was the cutoffs for strong. So which other picture has the points pretty closely tied to that line? And it's this one, right? So this one is r squared is 0.69. This is also a strong relationship. Technically, this is strong positive and this is strong negative, but the r squared values don't give you positive or negative. You get that from the slope. All right, 0.35. Now it seems like 0.35 is a low number, but remember, 0.35 is right in the middle of the moderate zone. So you're looking for a moderate relationship, one where the points are, close to the line. You can kind of see it. And that's this one right here, right? You can really see those points kind of near that line. So this is r squared equals 0.35. This is a moderate relationship. We've actually already done these graphs back in section 4.1, so you can actually verify them with the r counterparts that we found back in that chapter. Okay, now 0.19 is a weak relationship, right? So 0.19, that's weak, right? So it's perfect here, strong, moderate, weak. So the weak relationship is this one. It's still kind of got a trend to it. So this is r squared equals 0.19. This is a weak relationship. And if you remember G, we've seen G before. Let me push that paper up. This is no relationship. If you got rid of that line, you would never even know there was a linear relationship going on here. This is kind of a blob. It doesn't have a trend to it like the other graphs do. So this is 0.01. This is no linear relation.